Our team is here to provide value-focused geophysical services by delivering enhanced subsurface understanding and meaningful cost savings. We employ the most advanced industry equipment and custom-tailored geophysical solutions while concentrating on safe operations, reducing project risks. Our service is unparalleled in the geophysical industry. We are HGI. Our presenter today is Shawn Calendine, a geoscientist and development manager at Hydrogeophysics. With more than 15 years of experience in geophysical and electrical leak location technologies, his expertise encompasses projects at the Hanford nuclear site, in the mining industry, and many other industrial complexes worldwide. Shawn has published and presented papers on geophysics and leak location technologies and informs companies on the value of geophysical applications. HGI is a solution-oriented geophysical consulting firm and service provider to the environmental, engineering, groundwater, mining, and natural resource exploration industries. HGI specializes in the application of geophysical characterization methods, subsurface monitoring of fluids and geologic materials, and liner leak location. In this presentation, Shawn will be discussing geophysical characterization and subsurface injection technologies.
Thank you for coming. We are going to discuss mining geophysics and how geophysical applications are of great value to the mining industry, giving broader understanding of subsurface hydrological challenges on mine sites. Heap leach complexity, such as construction, reagent application, and heap hydrology behavior. Electrical resistivity technology and its ability to characterize the inner workings of heaps. And finally, the value of geophysical technology. Specifically, we are going to look at hydrological challenges in heap leach pads that have been revealed through geophysical characterization methods, allowing engineers to focus on problems through targeted mitigation. Keep in mind that even though we are discussing hydrological aspects of heap leach pads using geophysical methods, these same methods can also be used on other earthen structures associated with mine sites, such as tailings piles, earthen dams, pits, and of course, the earth itself. So what is geophysics? Geophysics is the scientific study of the Earth's internal dynamic structure. Geophysicists use geophysical tools and techniques to study near subsurface physical properties and the subsurface structure of Earth materials for industrial, environmental, and commercial needs. One of geophysics' greatest attributes is its scalability. For example, we can use geophysics to look at aspects and characteristics of the entire planet. This image is one of the GRACE satellite. GRACE stands for Gravity Recovery and Climate Experiment, which was a 15-year mission that flew twin spacecraft in tandem around the Earth to study key changes in the planet's waters, ice sheets, and solid Earth. Moving down the scale, we have regional airborne methods, such as electromagnetics, commonly referred to as EM, which covers tens of miles. Then we have the microsite scale, which can cover tens of acres. This is the resolution we will be discussing today. And then finally, we have the microsite scale, which covers borehole methods and CPT. So why use geophysics for the mining environment? Well, there are few ways to interrogate the Earth. Subsurface geological mapping doesn't always capture what's below ground. Traditional techniques are highly invasive and disruptive, such as drilling, which is expensive and very limited in its characterization area. Remember, Earth science isn't known for being data-rich. However, geophysics offers inexpensive insight with lots of data and is scalable to both large and small project areas. It can be used to help with a variety of disciplines, including environmental remediation, hydrology, civil engineering, geology, geochemistry, and of course mining. Geophysics gives the best value for targeting subsurface challenges by allowing engineers to react quickly and mitigate heap problems that would typically go undetected at great cost to a mining company. So let's take a look at heap leach pads. Remember, the geophysical methods and techniques discussed throughout this presentation are applicable to many other areas of the mining environment. This slide presents an idealized heap with 2 lifts and a small depression to the left, representing a recovery pond. Below this image are 5 smaller images showing the growth of a heap leach pad over time. In the final image, the finished pad could contain more than 400 million metric tons of ore. A lot of models consider this idealized heap as a primary and straightforward representation of a heap. This depiction severely underestimates the real and actual complexity that heaps present. For example, the first row of images highlights different stacking methods. The second row highlights different heap shapes. And the last row highlights heap height and grain size. Each of these characteristics needs to be considered when it comes to understanding heap structure and hydrological flow through a heap. The upper schematic is again a simplified heap model, but for this image, we have added blue to represent what we would consider uniform solution application and solution moving downward through the pile. The photograph shows different mechanisms for the application of leachate irrigation. All of the techniques are highly structured and attempt to distribute the reagent as evenly as possible. The methods seem uniform, right? For heaps, our observations seem to tell us that the ore is placed evenly, that it is a homogeneous mixture, that the irrigation methods are distributing solution equally across the pad. A rhetorical question. Therefore, shouldn't we expect that solution is propagating through the pad and wetting the entire structure uniformly? How do we know when all we can observe is something similar to this image? How can we possibly know from a holistic perspective that the subsurface pad is being wetted evenly? For example, with respect to the height and size of an engineered rock pile, a single drop of water falling on top of a heap leach pad could have a residence time within that pad of 3 or more years. The fundamental purpose of heap leaching is to move leach solution through the pad to dissolve valuable metals. Having product locked up within the heap environment for more than 3 years is problematic. A technology that can image your heap's internal performance would be a valuable asset to improving heap production. Here are some unwanted observable clues that solution flow has gone wrong. Surface ponding, seeps, slope failures, or drilling a well and bringing up water from more than 100 feet deep in the leach pad. So one of the ways to answer the question of how we can understand what is happening to solution flow in heaps is to use geophysics to look inside. This slide summarizes the types of flow we have seen in leach pads through using geophysical methods. The upper left is considered ideal, with the light blue representing water. The other illustrations have blue rectangles showing different subsurface flow examples we have observed in geophysical data. We have learned that geophysical characterization helps us visualize the flow happening within a heap is not uniform. It does not behave according to our standard simple model. For mining geophysics to characterize heaps successfully, geophysical service providers must learn and understand the entire leaching process and everyone's role in contributing to building and maintaining heap leach pads. We now know that rock piles have shown to be exceedingly complex due to the non-natural construction of earth materials. Therefore, successful geophysical characterization of rock piles requires the knowledge of many disciplines, such as process engineering, geotechnical engineering, mining engineering, metallurgy, geology, and hydrology. A successful geophysical program can help overcome the significant hurdle of understanding solution flow through heaps. HGI's mining characterization technology can map these internal flow regimes, giving mining operators a broad understanding of how and where to target mitigation efforts. For the remaining portion of this presentation, we will show you how this technology works with real examples of heaps characterized with geophysical solutions. Electrical resistivity is the method of choice we use to characterize subsurface hydrology in heap leach pads, as well as other areas of concern mine sites may present. This method involves making measurements using electrodes installed on the surface of the Earth, which allows significant flexibility in terms of non-invasive data acquisition. Electrical resistivity maps electrical contrasts related to the heterogeneity of soils, rocks, and moisture distribution. It easily characterizes imposed fluids. It helps us understand the unique internal structure. It gives insight into subsurface solution behavior, and it is a holistic approach with big picture appeal. If you consider the basic heap leach process, that is, that heaps are comprised of a massive pile of highly resistive material, earth and ore, and then a highly conductive solution is added, we then realize that this is a perfect scenario for the electrical resistivity geophysical method. This slide gives an idea of where electrical current is flowing as it moves through the subsurface. Most earthen materials can convey electrical current. The rate of current flow is related to the properties of the earthen materials, i.e., whether the substrates are resistive or conductive. Thus, electrical resistivity is a function of the following: moisture, ionic strength, ionic mobility, porosity, mineralogy, sedimentation, consolidation, tortuosity, and temperature. The resistivity method relies on fluid-filled pore spaces for electrolytic conduction. That is the fraction of water filling the pore space between the grains of earthen materials, and the fraction of pore space relative to solid grains. Remember, the more fluid within the pore space, the more conductive, and the less fluid, the more resistive. To capture the resistivity image, electrical current flows into the ground via a pair of electrodes, a transmitting dipole. As the current propagates through the earth, it is measured at a second pair of electrodes, the receiving dipole, which is at some distance away from the first pair. The received voltage is a measure of the electric potential of the subsurface at depth. Data are collected by the transmitter and receiver computer, which is programmed to switch between electrode pairs automatically. Note the schematic on the right. The distance between the transmitting dipole and receiving dipole determines the depth of data collection, such that a greater distance yields a deeper geophysical map of the subsurface. The survey design and viewing depth are tailored to meet the needs of the site investigation. The point cloud demonstrates the great volume of data that is acquired during resistivity surveys. The point cloud is turned into a visual representation of the survey area, also known as a cake slice or plot. Therefore, when fluid is present in the ground, there is a contrast in electrical properties between the native material and the intruding fluid. Electrical resistivity measurements can detect these contrasts and identify hydrological anomalies in the subsurface. In this image, you can see an example of where various targets in the heap leach pad were identified by a single resistivity survey. Note the colors representing conductive and resistive features. Blues and purples represent highly saturated conductive areas, while reds, yellows, and browns represent drier resistive areas. Light greens and blues are somewhere in the middle. In this example, there is a commonality among many heaps that we have imaged: densification. Densification is a significant issue that affects adequate drainage through the heap. In each of the plots, note the familiar location of highly resistive materials, reds, yellows, and browns, at the bottom of the heaps. This is densification. The purple and blue layers located in the middle of the plots are water tables that have developed above the lower, dense, and dry ore. Note, 3 of the heaps presented here were drilled to verify the location of the highly saturated materials. Because dense materials form at the bottom of large piles, ore tends not to drain adequately through the lower parts of the leach pad. If this is true, there will likely be metal left in the leach pad that cannot be retrieved through continued surface irrigation, no matter how long you leach. The water table that typically develops has special hydrological features that are adverse to the intended operation of the leach pad. I also wanted to show examples that not every heap has challenges. And these plots, the solution is more uniform where irrigation is happening. The top and bottom images are examples of crushed heaps. Active leaching is occurring where conductive features are at the surface. The middle heap is ROM, and irrigation is happening only on the first 375 meters. Here are some examples where heaps defy explanation into why flow is occurring as it is. We cannot conceptualize everything. Now that we have characterized the heap with geophysics and understand potential hydrological challenges, such as complicated heap structure which controls recovery, the fact that heaps are not a homogeneous mixture, they are in fact heterogeneous and not uniform in composition, that the internal structure cannot be predicted, and that one of the most damning issues that we have noticed is densification, which can vary through space and time. What's next? Injection. We can inject heaps to mitigate the challenges we see in our geophysical characterization results. We also use geophysical monitoring during the injection process to both optimize the injection program and make sure the injected fluid reaches the intended target area for mitigation. Injection is forcibly directing solution to where it naturally does not want to go. There are a variety of different names to the technology, such as enhanced metal recovery, secondary recovery, and subsurface leaching. In each case, reagent is injected deep into areas of the pad using specifically designed wells and delivery systems. There is low pressure injection with raffinate lines connected directly to wells and high pressure injection using pumps. Intensive monitoring is conducted to ensure safe and economical operations and includes time-lapse electrical resistivity monitoring, metallurgical monitoring, well hydraulics, and production modeling. Injection offers a unique and targeted way to liberate valuable product that may have gone unknown and unrealized without HGI's geophysical technologies. Now mine operators have a new and exciting way to recover excess metal inventory at a fraction of the costs. Here, we examine differing aspects between high pressure and low pressure injection. High pressure injection uses an external pump operating at greater than 10 bars with flows upwards of 300 cubic meters per hour, or approximately 1,300 gallons per minute. The wells are steel with multiple screen sections along the well. The wells have a wide spacing. Each well is operated individually, and rinsing is conducted before and after injection at a lower pressure. Low pressure injection uses a barren line connected to a wellhead, operates at 1 to 5 bars with flows around 45 cubic meters per hour or approximately 200 gallons per minute. The wells are PVC and single screened. The wells are spaced more closely together than high injection wells, and the wells are operated in groups and can be nested together for multiple depths. Here we have advantages of heap injection. We can get raffinate to deeper parts of the leach pad. There's also faster recovery. We can keep high flow through the plant, and we can leach side slopes. Non-obvious advantages are the displacement of antecedent pore water. That is, the existing solution in the pore space will be removed with the newly introduced injected solution. This older pore water has leached metal because it has been sitting there for a long time. We see a big bump in grade when we first turn on a system. There's also a change in the geomechanical structure. The schematic to the right highlights what happens to the ore when hit with high velocity solution. The small particles move away from the wellbore, i.e. washout, leaving behind a skeleton of large particles. This can help with future drainage. There is also more access to the heap for additional sensors or data about how the heap is operating. New instrumentation can be installed because there is a significant drilling campaign. Additionally, you can use the wells to add whatever reagent you need at specific locations in the heap, such as oxygen or milk of lime. Here is what injection looks like. Again, geophysics is used to track the injected raffinate. It is a very versatile tool. The examples below show low-pressure injection with time-lapse resistivity. The first image shows a 3-well injection. The middle shows a 4-well injection. And finally, the last image shows an injection using 6 different wells. Here is an example of an injection into a copper heap using time-lapse resistivity monitoring. This is an injection using 4 different wells. A short review and some final remarks. We have learned that heaps have a complicated structure, and that structure controls ultimate recovery. We have also learned that the structure cannot be predicted, but can be measured and understood with geophysical characterization technology. Also, the most damaging issue that we have noticed so far is densification. It can vary through space and time in heap leach pads. However, injection combined with geophysical monitoring is a new and extremely valuable tool enabling enhanced recovery of precious metals in heap piles. We use geophysical monitoring to ensure safe and economical injections, and we have shown through experimentation with injection on older heaps that additional recovery is possible at low costs. For example, over the long term, we estimate that gold recovery with injection can be accomplished at approximately $500 per ounce. And for copper, we can get the cost down to around 50 cents per pound. Thank you for listening. For more information on geophysical technologies from hydrogeophysics, email us at info@hgiworld.com or call us at 520-647-3315. You can also visit our website, which is also at hgiworld.com.